Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng Student. In this lesson we're going to take a look at something a little bit different. We got submitted a question by a high school student and the heading of the email was "This question is impossible." And on the face of it, when I read the question, I had no idea that this was even going to be a solution. I actually thought that the question was a bit of a wind-up. But after taking some time and really sort of focusing in on the sort of principles of maths, the solution is absolutely elegant. It's such a unique and really lovely solution that we had to create a tutorial and I had to share this with you. Now what I would ask you to do is have a look at the question, try it for yourself, and then comment your answer whether or not you got the same, or if you thought like me that the question was, on the face of it, absolutely impossible. So let's have a look at the question. The question says that one day it started snowing in the morning at a heavy and a steady rate. A snowplough started out at noon, going 2 miles in the first hour and 1 mile in the second hour. What time did it start snowing? Now, when I first read that question, I genuinely thought that it was a bit of a wind-up because there was no way I could see that this was actually going to be solvable. However, after doing a bit of digging, a bit of asking some questions here and there, I decided that it must have a solution. There must be some mathematical solution. And so the first thing that I did was break the question down into the key components. The first component is that the snowplough began at noon, which tells us that the snow must have started before noon. And it does sort of elude that in the question, but it has to be before noon. Now then we have a heavy and steady rate. And what that implies is that there is predictability in terms of how much snow is going to fall as a per unit time basis. And that's really going to help when we start to create the nomenclature for the solution. Now then we see that the snowplough goes 2 miles in the first hour, but then it only goes 1 mile in the second hour. And that relationship here is absolutely fundamental in order to establish the time that it took for the snow to fall. All four of these relationships is what makes this question solvable. Without one of these, it's impossible to solve. And so, the first thing that we need to do for this is set up the nomenclature. And this ultimately is the trick to this entire problem. If the nomenclature is not set up correctly, then there is no way that you're going to be able to solve this. And so let's set up the nomenclature. If you haven't managed to start the question, then feel free to use this nomenclature and then try and solve the question. Now, we're going to state that the time measured from noon in hours is denoted by t. X of t is going to be the distance the snowplough travels in miles. So you can see here that as time changes, x is going to change. So x is a function of t. Now we have h of t, which is the height of the snow, which we'll have in centimetres, and that's sort of the same relationship, is that as time progresses, the height of the snow increases. And then we have the rate of snowfall. And the reason we can have the rate is because in the question, it was heavy and a steady rate, which means we can have some sort of constant. Now we're going to give this the denotation of k, and we're going to have a few of these, so the k1 just indicates that it's the first rate. And this is in centimetres per hour. Now the thing that we want is the number of hours before noon. This is the thing that we are going to solve. So after we create our equations, when we create our model, this is the value in which we need to find. So we first need to express all of these terms as a function of b, and then begin to solve mathematically. So how do we start? The first thing that we want to do is establish the relationship between the height of the snow and the rate of the snowfall. And so what we can therefore say is that h dash of t must be equal to k. Now you might be saying, well, you said it was h of t and not h dash of t. And that is true. But because we are now providing this as a rate, we would have to integrate our system. This is actually a differential equation. So in order for us to establish the working relationship as a sort of linear equation, we have to integrate, because only by integration can we establish a relationship between 2 points in time. Now, what that will then allow us to do is determine the functional relationship between h of t and the rate. So, by integration, we can achieve the following. Integrate this is just h of t, and then if we integrate k with respect to t, then we will get k1t plus c. Now the plus c is obviously there because it is an unbounded system. It's an indefinite integral, and so we need that constant. So now we've expressed the height of the snow as a function of time and of the rate, which is really, really important. However, this is not explicitly stated, and it's also not a function of the variable that we want, which is b. And so we need to do some manipulation in order to A, remove the c term, we need to get rid of that, but we also need to have a way of getting b into the equation, because as it stands just now, that doesn't tell us anything about the time that the snow started. And so this is really, really important, is that this assumption here is that at point B, so B is time, the height of the snow must be 0 because it hasn't started snowing yet. So what that tells us is that minus B must be equal to 0, and that is fundamental to the solving of this problem. This is the part, and I'm not going to lie, this is the part here that really, really stumped me for a long time, because I could not work out how I could bring in the b term in such an efficient manner that we could do these things simultaneously. And so that was really, for me, a turning point in being able to solve this. So what we can then do is this, because again, this is a time parameter, and we're still working in the t domain, we're still working in time. So what we can then do is say, okay, we have the relationship we established previously. Now, if we then say, well, actually, instead of it being t, we will express it as minus b, because that's a time, that's before noon. So what we can then do is say, well, h of minus b would be minus b times k plus c. Now we know that when t is equal to minus b, the whole equation dissolves to 0. And so what we can then do is express our constant as k1b. So it's the rate times by the time that it started. And that's really, really powerful, because what that then allows us to do is express the height as a function that is independent of a constant, and it is a function of the rates, it is a function of time itself, and it's also a function of when the snow started. And that's us really starting to hone in on the problem. But we are a long way off from being able to solve this. Now we can tidy this up and we can take k1 out as a common factor, just makes it nice and neat. And so we get h of t is equal to k1 multiplied by t plus b. Because whatever the time is, plus b multiplied by its rate will give us the height. Fairly simple. Now, that's us dealt with the height. Now we need to bring in the relationship between the snowplough and the snow height. But what we can establish is from the question is that the snowplough's speed is inversely proportional to the height of the snow. Well, you might say, well, how is that the case? Well, if we think about it, it went 2 miles in the first hour, and then 1 mile in the second hour, which means as time progresses and the snowfall gets higher, the snowplough slows down. And so this functional relationship is what we can now start to exploit. So thinking about this purely algebraically, then what we can say is that x dash of t, so again the differential of the speed of the snowplough with respect to time, multiplied by the height of the snow, must be equal to some rate. And we're going to call this k2, because k1 is the rate of the snowfall, k2 is the rate of the snowplough. Now what we can then say is that we can we don't need to worry about these k terms, all right? These will eventually cancel themselves out, but we just need them so that the left and right hand sides of the equation are mathematically, valid. But don't worry too much about the rates, because these are going to be constant anyway. And so what we now need to do is, if we express x dash of t as a function of the height and the rate of the snowplough, then what we can then do is perform the same trick, and we can start to integrate this. But the good thing is, we actually know what h of t is as a function of t, k1, but more importantly, b. Because remember, b is the variable that we want. And so we can replace h of t with k1 over multiplied by t plus b. Now, because these k2s and k1s are constant, what we can do is just simplify it a bit and say that k2 over k1 is equal to k3. And that just simplifies the nomenclature a bit. We don't have too many variables floating about. Now, we do exactly the same thing in order to establish the functional relationship between the snowplow's speed as a function of time. Now, in doing so, the integral of this is obviously going to be xt. However, it's not going to be as simple as the first integration that we did, because we have some things that we need to change. And what we can do is take out k3 as a constant, because that's not going to change. And what we're left with is 1 over t plus b. Now remember, these are functions of time. And so, if you have 1 over these terms, then from simple mathematics, we know that is the log of the denominator. And so the speed of the snowplough becomes k3 log of t plus b plus c. Now we're still under this same constraint, is that we still have c, and it's not explicitly a function of time. And so we need to do some manipulations in order to simplify this. Now, we have 2 sets of conditions that we were given on the question, and this is a thing that we've already sort of exploited it, but now we're going to use the actual numbers to get rid of the c term. So we know that from 0 to 1, so from 0 hours to 1 hour, the snowplough travels 2 miles. And from 1 hour to 2 hours, the snowplough travels 1 mile. Knowing these, we can create 2 equations and solve them simultaneously. Let's first consider this condition here. So from 0 to 1, and it travels 2 miles. In doing this, what we can say is that x of t is the distance, so that must be 2. That's fairly straightforward. Now, what we then have to do is integrate this by substitution of the limits of 1 and 0, because that's our 2 conditions. Is that this is the integrated equation, and so now what we do is we substitute in the values of t as 1 and 0. And by doing that, what we end up with is when we apply a set of limits to an integral, you know that the c terms cancel each other out. which then means that we're left with this expression here. Now, it's still not 100% because there's a lot of simplifications we can do. For example, we have k3s here and here. We have log 1 plus b and log b on the right hand side. And so what we can do is use the laws of logs in order to simplify this. So when you take logs away, we'll obviously take k3 out as a constant, like so. And then we would do that. When you take logs away from each other, you divide them. And so we get 1 plus b divided by b. That there is equation number 1. Now we do exactly the same thing, but for the conditions between 1 and 2 hours that the snowplough travels 1 mile. So x of t is 1, and we use the limits of 2 and, sorry, that should be 1. And then here, we substitute them in. You can see that the c's cancel each other out, and we'll do exactly the same trick, and this becomes equation number 2. So now, equation 2 is 2 plus b over 1 plus b, the log of that, and you can see what's going to happen, hopefully, in just a second. So, we now have these two equations, and we're slowly approaching a point where we can solve for b, but we need to sort of eliminate the k terms, and we need to somehow eliminate the logs, because we're almost there. Now, is there any trick that you could see that would allow us to equate these equations together? Because as it stands just now, there's nothing that would allow us to do that, except if we multiply equation 2 by 2, then watch what happens. Equation 1 stays the same, but equation 2 then has 2 equals this, but 2 also equals that. So what that means is that we can make these two equations now equal to each other. And that's really, really powerful, because now we can start to simplify this. Using the laws of logs, we can move this 2 to the power of the bracket. So this becomes, that's the sort of, there's different rules in logs, and different people call them different things. But sometimes it's called, I think it's called the fly rule, where it sort of flies from being a scalar and it rises to becomes a power. And what this then allows us to do is we can start to cancel out the k3s. Because if k3 is on the left and k3 is on the right, both of them cancel. And then the logs cancel. So we are so close to solving for b. Right now it looks an absolute mess because we have 4 b terms and we have these raised to the power 2. And genuinely, when a lot of people solve these questions, this is where they get stuck, because they can do all the fancy maths, but when they get to the algebra that needs to be simplified, they end up making up their own rules. And so you have to be very, very stringent and very strict and only use mathematically valid rules. Now, I say simple. It's not entirely true. It is a fairly complicated system to sort of simplify, but in the grand scheme of things, it's fairly straightforward from this point, and hopefully you can see where this is going to go. So what we can do is separate these terms, the numerator and denominator, and give them their own squared bracket. And what that then does is we have 1 plus b squared. We can cross multiply these, and what we end up with is 1 plus b cubed, and then b times this bracket here. Now, let's sort of expand these out, and let's see what happens. So if you were to take 1 plus b cubed and break all the brackets, you'd end up with 1 plus 3b plus 3b squared plus b cubed. Now break this, so you would break the bracket 2 plus b squared, and then multiply everything by b, and you end up with this on the right. Now we can start to simplify. The b cubeds disappear, And we can then have, if we've got 3b squared on this side and we've got 4b squared on that side, then of course, we can cancel them out. We've got 4b on this side, 3b here, and then plus 1 on that side. So if we arrange these, we end up with b squared plus b minus 1 equals 0. Now, from those that have got to this point, what type of equation do we have? Well, it's a very simple quadratic equation. So simple now that we are almost there, because you can now see that applying the quadratic equation, if we say a is 1, b is 1, and c is minus 1, it just becomes a number substitution. So we substitute in the values of a, b, and c, and we end up with minus 1 plus or minus the square root of 5 divided by 2. Now remember, you have to break these apart. So we get two equations. And then the question becomes, we get b is 0.618 or b is minus 1.618. Now how do we know which one is correct? Well, b is a time parameter, so it has to be the positive value. We can't have negative time. And so we have now established what b is. And remember, b is in hours. So what we have to do is convert 0.618 hours into minutes. If we multiply it by 60, we work out that it started snowing 37 minutes before noon. And so the snow began at 11:23 a.m. Now comment your answer if you got 11:23 a.m. or if you didn't, comment what you got. Because to start with, I had some very strange answers, I'm not going to lie. But you can hopefully see and appreciate just how eloquent that this solution really is. I thoroughly enjoyed solving this. Even though it caused me a lot of headaches, I still really enjoyed it. And I hope that you enjoyed the solution to this as well. And I highly encourage you to share this video and let people see just how pretty maths can really be. You take a problem that seems impossible, you give it some time, you give it some conditions, and you solve it in a systematic way. So you can see that maths can make something that seems impossible actually possible. So that's the end of this lesson. Thank you very much for watching. I hope that this was informative, enjoyable, and you enjoyed it as much as I did in solving it and finally being able to share it with you. If you liked this video, please like, subscribe to the channel. It really helps us reach as many students as possible, and we're really trying to hit 10,000 subscribers by the end of the year, so I really appreciate your time as well. If you'd like to connect with me on LinkedIn, then you can scan the QR code here, and please do feel to get in touch. I always like to connect with our viewers. And thanks for watching, and we'll see you in another video.